And thank you all for joining today. This is our last webinar. So we hope to, schedule some periodic webinars during 2023. So watch out for those. But today, I am the presenter. So generally, I will have somebody else present it, and I can just relax and listen to that. But today, I am in a hot seat. But I'm glad that you all have joined today to listen to me. So the presentation today, I'm going to talk about this leachate recirculation and bioreactor landfills. All right. Some of you may already know about this topic. Some of you may not have heard about this topic. So, in light of having wide expertise in the audience, so I'm going to just cover some basics, and at the end I want to cover about some of the research that we are doing on this topic. All right. So as you all know, I'm Professor Krishna Reddy from University of Illinois at Chicago. So this is my email address. You can feel free to contact me anytime after the webinar, or so anytime in the future. So what we are talking about is landfills. So this is the conventional landfill design. Many of you probably already know this one. This is the minimum requirements for a landfills in US, and most of the other countries have adopted the same thing. So the US regulations say that you should have a bottom liner and side liner leachate collection system on the top of it, and then you put the waste, and then you have to have a final cap on the top. And then in addition to this, you have to have a gas collection system, and then you have to have a groundwater monitoring system. So the landfills, as they are designed, based on these requirements, are found to be working very well. So any leachate that is generated within the waste that comes into the leachate collection system in the bottom, and then that gets removed, right? The final cover will not allow any infiltration of the precipitation or rainfall, so you not introducing any additional liquids into the waste. So this is sometimes we call subtitle D landfill, because subtitle D is kind of a section in a law called Resource Conservation and Recovery Act, called RCRA. And these are all specified as the minimum requirements. As you see, some thicknesses and hydraulic conductivity requirements are number of layers. The materials are specified in this one. These are also known as dry tomes, because you're not allowing any moisture to be collected or retained in the waste itself, because any leachate that goes to the bottom, that gets removed, and you're not allowing any infiltration of rainwater or any kind of water getting into the waste. So these are all in 40 CFR Part 258. Those are the regular requirements. You can look at it. So many landfills have been designed based on this criteria, and they are in operation. Many of them in US for over 2 decades, 3 decades. And there is a lot of monitoring data that shows that these designs are working perfectly. So there are no issues in terms of the groundwater contamination, based on these designs. So then the question is, yeah, it's working very well, but now everybody's thinking about sustainability. Is this a sustainable option? So if you ask that question, then we need to think a little bit more about what we are doing, and if there can be anything that can be done to improve the things. So one of the problems with the current situation is that since we're taking out all the leachate from the bottom, not allowing any leachate to be accumulated in the waste. And also we are not allowing any water to enter into the waste. So the waste is generally in dry condition. So as a result of that, you don't have very optimal conditions for degradation to occur. So you have microbes in the waste, and they want to degrade the organic matter, but they need certain moisture content to do their job. So since you have very low moisture content, so the degradation rates are going to be very slow. If the degradation is slow, because of the degradation, you can generate the gas, and then, because of the loss of solids, you're going to have a settlement. So all those things will happen very slowly. So you're going to have a low gas generation, basically slow rate of gas generation, and the slow settlement rates that will happen. So what does that mean is it will take very long time for the entire gas to be, emitted, and entire settlement to take place. Basically, the settlement and gas is related to organic content in the waste, and all the organic content will degrade very slowly. So it will take a very long time for this stabilization to take place. The other thing is the leachate treatment and disposal costs. So as I mentioned, leachate is collected at the bottom, and then they're removed and treated on site, or generally, sent to a wastewater treatment plant. And you have to do this one continuously, for a long period of time, because, the waste is degrading very slowly. So you're talking about, long-term commitment for doing this one. And then, you have to also, once you close the cap the landfill, you are obligated to monitor the landfill for 30 years or more. So you will have a more, post-closure monitoring costs, as a result of waste not stabilizing it, and the need for monitoring the gas and the leachate, and then groundwater monitoring, all those things. And then, increased greenhouse gas emissions over a long period of time. So even though you have a final cover, there could be fugitive emissions, and you will have greenhouse gases emitted over a long period of time. So these are kind of issues if you look deeply into what is going on with the current practice. So as a result of these issues, the concept of the bioreactor landfill came into picture. So other aspect is, if the waste is going to degrade a long period of time until waste degrades, until the waste stabilizes, you cannot really do anything, with the landfill. But if you stabilized it, perhaps you can use the site for some beneficial use. So that's also another concern. So to address all these issues, the concept of these bioreactor landfills came into existence. So what is this bioreactor landfill? So bioreactor landfill is basically same as subtitle D landfill. So you have this bottom liner, you have a leachate collection system, you have a final cover. So everything is as we are doing, okay? The only thing is, right now we are basically taking out the leachate and treating it on site, and disposing of the treated water into the surface waters, or taking it to a wastewater treatment and treating it. So, but instead of doing that one, in the bioreactor landfill concept, you collect the leachate and store it if necessary at the site, and then inject in a controlled manner into the waste, using either series of vertical wells, or you could have horizontal wells. So basically, you are trying to inject the collected leachate from the bottom, into the waste. The idea is to be able to distribute the leachate uniformly across the waste. The idea is to increase the moisture content and create conditions that are conducive for enhanced biodegradation. So remember, before we had a low moisture content, that's the problem. So now we are increasing the moisture content through this recirculation. In addition to the moisture, you have benefits of higher microbes and nutrients. You will have other benefits that cause higher degradation of the waste. So just simply collecting the leachate, instead of sending it to the treatment, you can re-inject into the waste and get all this accelerated degradation, and that provides a lot of benefits. The primary benefit is you will have a rapid waste decomposition. And as a result of this rapid decomposition, you're going to have a gas generation rates, increased generation rates. And then since gas is generated faster and substantial amount, you can consider waste to energy projects feasible. And then you have high settlement rates because you want a settlement, to be occurring really fast so that you can use the site for some beneficial use, and early waste stabilization. So you're talking about waste taking maybe 30 years or more for degradation. Can we reduce that time to maybe 15 years, 20 years, or even less than that time period? So these are the primary advantages. In addition to that, we will have a lot of secondary advantages. So you have a reduced post-closure monitoring cost, because if you are stabilizing in the waste in 15 years, you don't have to do the post-closure monitoring after that, maybe, right? Depending upon the conditions that you have 15 years down the road. But otherwise, in a conventional situation, it's going to take more than 30 years, so you still have to keep monitoring it. And then, this leachate recirculation, what happens is when you collect the leachate, that will have a lot of organic strength. As a result of that, a lot of wastewater treatment plants, they don't want to accept the leachate, even if you want to pay them for the treatment, because their systems are not designed for this such a high organic strength liquids, right? Water. So you will have a lot of issues with getting rid of that, high organic strength leachate. But here, you have to basically simply doing the leachate recirculation. That organic strength actually might even benefit in enhanced degradation. And then, since you are not sending the leachate to wastewater treatment, or you're not treating on site, you are reducing all the costs associated with that. You're almost eliminating the costs associated with treating the waste, treating the leachate. And landfill space reclamation for fresh waste. So if waste is degraded, perhaps you can do the landfill mining and create the space for that. Or even if you're doing this leachate recirculation operations during the operational periods, if you have a settlement that happens, and then you can put more waste to in that saved space as a result of the settlement. And then at the end, if this degradation happens really fast and all the organic gets converted into gas and removed, then you only have inorganics, and we can go into landfill mining and recover any usable materials out of that. So this has a lot of benefits, right? I mean, as you see it, why not do this one instead of just making a good containment and watching for a long period of time. So this, in fact, if you do this bioreactor landfill operations, you are converting this into like a treatment system, and as well as a containment system. So you have a containment system, as well as it's a anaerobic biodegradation treatment system that is happening at the same time. So this is a very, very good, and a lot of attention is being drawn for this technology to be used. So, but one thing you have to be careful, when you're talking about bioreactor landfills, is that the prerequisite for having bioreactor landfill is having an engineered landfill. Okay, so I've seen people where they're trying to do the bioreactor landfill concept where you don't have an engineered landfill. So it's very important to control that leachate at the bottom of the landfill. Otherwise, you're going to create a lot of subsurface contamination that will lead to a lot of issues. So in US, this bioreactor landfill concept is considered to be very good, but there's a lot of caution in terms of how we can use it. So US EPA, which is the responsible agency in the US for environmental pollution control, they have been working on this one for a long period of time. So they realize this important, but there's not much information in terms of how this can be operated, how things happen, so they wanted to start slow, and they right now you cannot really inject leachate or any type of liquids into the waste. But they came up with this approach, case by case, based on this RD and D permit. So if somebody is interested in converting their landfill as a bioreactor landfill, they need to apply to US EPA, get this research demonstration and development permit. Then only you can do it. And in the regulations, you don't find a universally accepted definition for bioreactor landfills. One definition that you can find in the regulation is given here. It says that MSW landfill or portion of MSW landfill where any liquid other than the leachate is added in a controlled fashion into the waste mass to reach a minimum average moisture content of at least 40% by weight. So this is kind of one definition, but there are no universally accepted definitions that you can see. So the situation right now is that the US EPA will allow state agencies who are responsible for enforcing the environmental laws can allow leachate recirculation. That can be done. So that's not a problem. But if you want to use any other liquids, then you have to get this RD and D permit. And the US EPA is considering additional regulations on landfills so that bioreactor landfills can be promoted or practiced properly. So they are concerned about of course the stability and environmental protection. So they are trying to take slow steps to make sure that when the bioreactor landfills are operated, then we don't have any environmental issues. So EPA has done some projects to get data. It's called Excel projects, basically excellence and leadership bioreactor landfill pilots. And then they have also done EPA state of the practice bioreactor landfill study. And they have also done with Waste Management Incorporated that owns and operates many landfills, some research on how best you can operate bioreactor landfills. So one of the things that you have to think about is that this waste degradation happens really fast, and this has been proven many years ago. So Poland in 1975, when he was at Georgia Tech, he did these simple experiments. Basically, he took a waste in a big column, and he recirculated the leachate, and he found out that the leachate comes out, gets cleaner and cleaner with time. So because that leachate is going inside, and then you have this the biological activities that is taking place, and then the leachate comes out to be clean. So here you see the chemical oxidation demand, and with time you see with the leachate recirculation. So after a certain period of time, you will see nothing in the leachate. So basically, leachate is getting cleaned up by leachate recirculation, and then of course the waste is degrading, and you're getting all these added benefits. So there is a sequence of the reactions that take place, and these are all well studied. You can look at the literature on these things. And then again, how the waste gets degraded under anaerobic conditions that prevail in the waste. These also have been studied extensively, and there are different phases that happen, degradation, and the end products of all this degradation is finally you have a methane and a CO2. So again, you can find, this is the classic work that was done many years ago. Still, it is valid, but you need to really be careful about what kind of waste composition you're starting with, and that could change some of these reaction pathways. So ideally, we want to have enhanced waste degradation. So waste degradation can happen if you have ideal conditions. So for example, moisture should be the fill capacity of the waste, or 40 to 60% by wet weight. So that's, if you have those conditions, you will have enhanced degradation. And the microbes don't like, the very low pH or very high pH. They like a near neutral pH. So, how do you maintain that? Temperature has to be, certain range for the microbes to be active. And sometimes you can add this inoculum to increase the microbial population. And these microbes need some nutrients. And you also want to make sure that you don't have any inhibitors that reduce the activity of the microbes. And then, you need to have a good contact with the substrate and microbes. So organics that you have in the waste and the microbes, should have a good contact. And then, the moisture flows. So, when you have moisture gets distributed, you're flushing out all the inhibitors that could be present, or, it could be acids. You're making sure that they are diluted to be favorable for, microbial degradation to happen. So we are saying that, hey, leachate, you take it up from the bottom and then distribute into the waste. Okay, that's just the moisture content. But we really need to look at all these different aspects and make sure that we have favorable conditions. So this is where, the decisions have to be made. For example, okay, leachate recirculation is basically you collect the leachate and then distribute. The bioreactor definition in a broad sense is that you can put any liquids. It doesn't have to be just a leachate, right? So if you use any kind of, the liquid waste, so for example, industrial liquid waste, landfill owners like to do that one because they can generate revenue for themselves, right? If they can accept the liquid phase from industries which are very hard to treat, if you can bring them and use it for recirculation, but make sure that these conditions are maintained. You don't want to, for example, if you get some industrial liquid and it has a lot of toxic metals, and you may be killing the microbes. So you have to be very careful in terms of what liquids you inject. So as I mentioned, there's the distinction between leachate recirculation landfills and the bioreactor landfills. Leachate recirculation landfills are the landfills where the leachate that is generated right in that landfill is collected and recirculated. Okay, whereas bioreactor landfills is that includes the leachate recirculation, and it also implies that you could be injecting other liquids along with the leachate. So that's the difference between the leachate recirculation landfills and bioreactor landfills. So everybody wants to do this one, right? As I said, landfill owners really love this one because they are saving the cost for leachate recirculation, leachate treatment. So, but there are a lot of practical issues in dealing with these bioreactor landfills. The first thing is leachate injection and flow in the municipal solid waste. So the idea of leachate injection is to increase the moisture content to its field capacity or to the optimum moisture content range. But we want to make sure that this moisture distribution happens uniformly in the waste, right? So how do you do that one? It's not easy, because waste is highly heterogeneous. And when you put in, leachate, you don't know where it is going, So it's a big challenge. Then the other thing is in geotechnical engineering, everyone knows that, the pore water or pore water pressures are the culprit for many failures. So here, what are we doing? We are injecting the leachate under pressurized conditions that could actually, endanger the stability of the landfill slopes. So you could have a leachate seeps, and you could have a slope instability and failure issues if you don't inject in a proper controlled manner, right? So that's other practical issue. And maintaining the optimum conditions. As I showed you in the previous slide, how do you ensure that you have optimum moisture content, say, pH, temperature, nutrients, and all those things to be favorable for accelerated degradation. And also leachate head levels over the liners, okay? So one of the rules for landfills is the leachate head over the landfill bottom liner would not exceed more than 1 foot. That's the regulatory requirement. You cannot have accumulation of the leachate. Even in case of bioreactor landfills, you have to maintain that criteria. So you cannot have a leachate head more than 1 foot. Because if you have more than 1 foot leachate, there is a potential for groundwater leakage into the groundwater because of the high hydraulic gradient across the liner. So and you have to be able to remove the leachate. So how do you handle all these things? Also a practical concern. Now, other important thing is the waste decomposes really fast. So the gas generation is, occurs really earlier than conventional landfills, and you're getting substantial amount of gas. So you have to put these gas collection systems, much sooner than conventional landfill conditions. And also, you have to do extra surface emission control and monitoring, because you don't want these any gases that are generated not captured. And you could have issues with compliance with the regulations. And you could also have a differential waste settlement due to mass loss, basically organic mass loss. You want to make sure that when you inject the leachate, if you don't get the leachate distributed uniformly, wherever you have high moisture, you may have high settlement. Wherever you have low moisture, low settlement, that will lead to differential settlement. If you have a differential settlement, you have a leachate recirculation system within the waste, that could be damaged. So you need to make sure that the leachate recirculation systems are fine. And then you also have a liner and cover systems are stable, because a lot of times in conventional landfill you assume that uniform deformation, but that's fine. But in case of these bioreactor landfills, you have to worry about differential settlement and how that could affect the liner systems, including geomembrane liners in the final cover. Those needs to be looked into. And then one should realize that as you are injecting the leachate, as the waste is degrading, basically solids are disappearing in the gas phase, and then the properties of the MSW will change. The hydraulic properties will change, mechanical properties will change, because what you started with, a certain solid composition is changing, right? So the porosity is changing, void ratio is changing, unit weight is changing, stiffness is changing, shear strength is changing. The geotechnical engineers, they assume the properties of the soils remain constant, right? But in case of municipal solid waste, the whole material composition itself is changing. So you have a very dynamic system that needs to be captured if you are doing any kind of analysis. The odor control, temperature, chemical compatibility of liners, liquid availability, operator skills. There are many other issues that needs to be taken care when you are implementing these bioreactor landfills. So the bioreactor landfill concept is very, very good. But these are all the practical issues that have to be paid full attention, right? So if you don't do this one, then you could have bigger issues than not doing it all, right? So if you want to go into the bioreactor landfill concept, if you want to implement it, you really have to do it properly. So in terms of the moisture, or the liquids that you can use, as I said, landfill leachate is the one that commonly used. There are no issues using the landfill leachate, but in a true bioreactor sense, you can use these other industrial wastewater sludge, biosolids, groundwater, or even stormwater. But even if I want to use clean water to recycle in the waste, that needs the permission also from regulating agencies. So you cannot just even use the clean water for leachate for recirculating in the injecting into the waste. So as I said, landfill leachate is permitted by a lot of state agencies. But if you want to use any other liquids, you have to have a special permission, a special permit to do that. So how do we inject the leachate into the waste? So there are several surface leachate addition systems. So you can use the drip irrigation. Basically, as you are placing the waste, you can have a drip irrigation system to distribute the leachate onto the waste. Spray head application. This is also commonly done. Tanker truck application. Basically you're injecting disposing the waste, and then in the tanker truck bring the leachate and put it on the waste that is just placed. Other options are surface infiltration ponds that are not commonly used, but you can also have a shallow surface trench or deep surface trench. But out of all these things, a tanker truck application or sprayed application, you can you think of those as a practical ways to add leachate as you are placing the waste. So this can be done, but other option is putting the vertical wells. So basically, how you construct your typical piezometers or monitoring wells, drill a borehole and put in slotted pipe, and then some filter media around it, and then seal the top with the bentonite, and then when you inject it, it's going to be distributed through this slotted pipe into the leachate. So this can be done after the waste is placed, or even in existing landfills that don't have a bioreactor operations. So you can install these wells and then inject the leachate into this one. The other common system is the horizontal trenches. So basically, as these have to be installed during the waste placement. So when you are placing the waste, after a certain height, you dig a trench, and then you place the pipes and you put a drainage material all around it, and then you inject the leachate from one end, and it's a slotted pipe. So as you inject it, the leachate comes out from this pipe and gets distributed around the waste there. So you have to have a series of these trenches at different locations so that the waste is uniformly wetted by the leachate. So this, you have to have a pre-planning if you want to go with this one, because you have to put these trenches during the waste placement. There is other leachate injection system. This is called drainage blanket. So after you place the waste up to a certain height, let's say, then you put a thin layer of drainage material. It could be gravel, it could be shredded tires, and then you put a series of pipes in it, and then you inject the leachate into this one. So when you are injecting into this one, basically, the leachate gets distributed through this hypermeable material, and then it infiltrates down. So you have larger area for infiltrating the waste into the waste. So this is another option. But most commonly used options are the trenches and the vertical wells. So we know what are the different types of leachate recirculation systems that we can use. Then, if I want to design a bioreactor landfill, what should I consider? The first thing is you need to think about how much leachate I need for recirculation, right? So what is the target moisture? So yeah, as I said, it's the field capacity, or 40% or 50% moisture content, whatever you determine. You have to look at what is the existing moisture content, what is the additional moisture that you need. You need to calculate that one, right? So there's some moisture content get lost by degradation reactions. And where is the source of moisture supply? Is the leachate that you have is enough, or you have excess leachate? What do you do with that? So first of all, make sure that you have leachate required leachate available for recirculation? So that would be the first question you will ask yourself when you are designing this one. The second one is, rate of leachate injection. How much I want to inject, right? Let's say you have a leachate injection systems, but how much I want to put it into this one. So that depends upon the leachate availability and leachate pumping capacity. How much you're going to pump it out, how much you're going to pump in, and then also it depends upon the waste properties, right? So initially the waste may be highly permeable because it's not degraded. You could inject large amounts of leachate, but as the waste degrades, hydraulic conductivity decreases, and you cannot pump as much as you want because it's a low permeable. It becomes less permeable, and you cannot really inject high quantities of the leachate at high rate. And then what is the type of leachate recirculation system that you have? As I mentioned, you have trenches and then vertical wells. Those are common. You need to look at the cost benefit analysis. What materials that I have? What is the construction materials that I have? And maybe you can use the combination of different leachate recirculation systems. So I've seen people, using the surface spray and also having the trench system combined. And then configuration of the layout of leachate recirculation system. So if I want to have a drains or vertical wells, what should be the spacing? What should be the depth? How many, I need? So this is a calculation that is very important. A lot of landfill designers, they want some information, some way they can calculate these things. So right now, you don't have proper guidelines on selecting, the spacing of, whatever the type of leachate recirculation system that you want to use. And the stability is a big concern. So don't get excited about, injecting a lot of leachate, but it could have a lot of negative consequences, right? So you want to make sure that, the leachate recirculation system itself is stable, because, you could by wetting the waste, you are increasing the unit weight, you will have access to overburden stress. And you could have a differential settlement, so you make sure that the pipes are not damaged as a result of that, and the slope stability. So you need to make sure that, especially near the slopes, if you are injecting very close to the slope, and if you are injecting at high pressures, then the slope could fail. So you need to maintain some setback distance, and then you need to decide what should be the acceptable pressure so that you don't have a slope stability failure. And the leachate collection and removal system. So you need to make sure that you have a way to handle the leachate. So if I am having a landfill with excess leachate, should I store it on site? In some cases, you don't have that much leachate generated, so you don't have any issues of storage. And then make sure that your leachate collection system works very well, because if you have a clogging issues, you will not be able to, collect it, and then that recirculation system become inefficient. So the liner system, you need to make sure that the liner system is designed and make sure that leachate collection system is also designed properly, so that leachate head never exceeds 1 foot above the liner. And then you also want to check, liner temperatures, chemical compatibility. So all this, waste interaction with the liner interface, all these things have to be looked into when you are designing these bioreactor landfills. So most of these things, we do it for typical landfill also, but you really need to pay a little bit more attention to, when you are doing the leachate recirculation systems. And then slope stability, many, attendees are geotech people. So this is the big concern, right? The two concerns are, okay, you cannot have one set of waste properties and do the slope stability analysis and say, I'm done. Because the waste properties are changing with time, right? Changing with the degradation. So unit weight that you have started with, that won't be the same thing as, maybe a year from now, from the leachate recirculation. 2 years from leachate recirculation. With time, with the biodegradation, this unit weight is shear strength is changing. So the whole properties are changing. So how do you do the slope stability analysis, right? You cannot assume one fixed values that you calculated for initial waste and then assume that the things would be safe after that. That's not necessarily true. And the other thing is, you are doing this dangerous thing of leachate injection under high pressures, which could be the reason for slope failure. So you really need to make sure that how much excess pore water pressures I'm generating, how much gas pressures I'm generating. So that's an important design consideration. Capping and cover. So when you put the capping on the top, right, you have a gas collection system. So the gas is being removed, and you have leachate injection wells that's going through the top final cover, and make sure that the final cover is is stable in spite of your differential settlements that could happen. And you have a gas extraction collection system. So make sure that they are designed to extract estimated increased gas production as a result of leachate recirculation. Make sure that you have gas pressures controlled, and so you want to make sure that this is another issue, because if you wet the soil, wet the waste excessively, let's say you saturated the waste, then you will not be able to collect the gas. So you need to make sure that the waste is never 100% saturated. So you need to have maybe let's say 80% saturation, so that you could have the air gas collection that would happen at the same time. So deciding this leachate recirculation systems spacing and the pumping or injection pressure or injection flow rate are very critical. So as I mentioned, there are no guidelines on these things. So several years ago, we did some modeling, hydraulic modeling, and then we created these design charts. At least you can, right now people don't have any resource. They just randomly assume, and then okay, 300 feet, 400 feet, whatever spacing they use randomly. But at least these design charts should give you some idea about the typical spacing, depending upon how much pressure that you're applying. So this is for design of horizontal trenches. I have given some example calculation here and also a reference here. So you can use this these non-dimensional charts to estimate what is the spacing and what could be the pressure that you can apply. We did the same thing for vertical wells. So you can use these design charts to estimate what should be the spacing of these vertical wells and what should be the injection rates or pressures that you can have, right? And this is the third type is drainage blankets. Again, we did this kind of parametric numerical modeling, develop these charts, and then you can use these charts to estimate what should be the dimensions of this drainage blanket. So at least I talked to a lot of landfill owners, operators, and I asked them what kind of information they need if they have to operate bioreactor landfills. So the first thing that they want to know is how to design this, how do you space this leachate collections recirculation system. So what should be the spacing? So I think that these kind of information should be useful to them. And then other thing is the setback distance, right? When you have slopes, where do I look at and what should be the pressure? So the setback distance is what is the minimum distance to your leachate recirculation system from the slope, okay? And what should be the pressure? So we did this again parametric modeling, and we came up with these design charts that will help you. Okay, the location, setback distance from the slope, and then with the maximum pressure that you can apply without endangering the slope. So again, this would be very useful. So I have a reference here. You can look at it for more information. So what, even you designed it and then let's say, went into operations. So you have to think about a lot of things. Okay, leachate availability. So, do you have a leachate that you expected, right, in your design? And what is the leachate collection removal system efficiency? So are you able to, remove all the leachate that is generated, right? Can you store the leachate at the site? You need to think about this one as you are operating it. Leachate injection operations. So leachate can be injected continuously or intermittently. And remember, if you have a landfill, you have a large area with a lot of these leachate recirculation systems, wells, or the trenches. You don't have, you may not have a lot of leachate to put it into every leachate recirculation well or trench, right? So you basically choose certain trenches or wells and you inject them, and then you rotate them, maybe change it to other one. So what happens is at any given location, you are applying the leachate, in an intermittent manner. So you're applying, let's say, for a week, and then, next 2 weeks, you're not applying it, just like depending upon how the landfill leachate recirculation system is laid out, and also how much leachate that you are generating. And then you need to have some people who knows how to operate these systems. Operator skills are very important. So this is where things could go wrong. If the guy who is doing this operations, injection operations, if he is doing excessively or not planned properly, you could have slope failures and all kinds of other issues. And the materials that you want to use in leachate recirculation system, make sure that they are chemically compatible, they have enough strength, so they won't get damaged during the operations. So remember, waste is highly heterogeneous, right? So some places you may have low permeable waste, and some places you may have high permeable waste. So sometimes the leachate could accumulate on the low permeable waste, and then that creates the purged conditions. So you need to make sure that those things would not happen. Sometimes this purged leachate could cause some slope stability problems. The gas extraction, you need to, you're going to be extracting high amounts of gases, so your system should be able to handle those things. And then, maintenance is important. As I mentioned, oversaturation of the waste is not desirable, because if you have that, then gas collection decreases. Seepage control. So if you go to landfills that are operating as a leachate recirculation wells, you might see, along the slopes, some seeps like this. So that means, they're not really, designed and operated properly. So you need to make sure that those things are not happening. If they're happening, so immediately, look at your design and operations and make corrections for that. Odor control. So especially this could be a huge problem. Depending upon the waste, you could have, for example, H2S that could smell bad, and with the waste accelerated degradation, you could aggravate these problems. And if there are people living close by, they're going to complain a lot. So you have to make sure that those problems are not there. Differential settlement, you need to watch out. As I said, differential settlements could cause damage to the leachate recirculation systems, liner cover systems, and stability of the slopes, and liner head and leachate collection and removal system is working properly. And then you need to record and record all the data, inspect and record all the data that you have during these operations. So that's very, very important. And then you have to also do the monitoring. So your operation basically involves, injecting the leachate, but you need to do this monitoring, how much leachate generation and its quality. How is the moisture distributed? That's the biggest thing. The leachate generation and its quality, you can do that by taking the samples and measuring the volumes that you're using it. But how do I know, how my injected waste is being distributed in the waste? This is a huge challenge. Some people have used some sensors, but putting sensors in the waste is a big challenge. What type of sensor, how do they, respond to, the settlement and all those things. Waste condition, how the waste is changing. So you want to see, whatever you're doing, is it making, is it doing what it's supposed to do, right? We are thinking about waste stabilization and how the geotechnical properties are changing. Waste settlement, we need to monitor that one. And the gas quantity and gas quality, we have to monitor that one. So these are all will help you understand, if bioreactor landfill is working as, it is designed. So temperatures also, you need to measure it and see. So all those things have to be monitored and then, take the proper, actions to correct any issues. Now, the cost issue, right? So does the bioreactor landfill cost more than a conventional landfill? So you have a construction cost, right? You have to construct it. And then you have operational costs, so then you have post-closure costs. So the landfill costs can be divided into three types. So if you look at conventional landfill, so you will see that construction cost is really high. Construction cost is high, and then you have operation and maintenance, and then you have a lot of cost for leachate treatment, and then you have a post-closure, right? So if whatever the cost it is, this is how these costs are distributed. Now, if I have a bioreactor landfill, obviously, initial construction cost is going to be slightly higher than your conventional landfill because you are putting this leachate recirculation system. So that's an additional thing that you're doing. And then operational cost is going to be higher than conventional landfill because you have, injecting the leachate, you have pumps, and you have people around operating that one. The difference here is this post leachate treatment. This is the leachate treatment cost. Leachate treatment cost is going to be very, very low in case of bioreactor landfill, whereas in conventional landfill, leachate treatment costs are very high. Okay, but then the post-closure costs are relatively shown here. So they will not cost the same, but whatever the total cost, the distribution is like that. So the overall cost may be low for a bioreactor landfill compared to the conventional landfill, but in terms of the cost distribution, so you save a lot from leachate recirculation, leachate treatment, and also reduce the post-closure cost associated with the bioreactor landfill. So overall, okay, in the life cycle cost, bioreactor landfills are going to be much cheaper than the conventional landfills. Also, benefits, other benefits, because if you have a conventional landfill, the gas production is very slow and small amounts, so you cannot really, it's not feasible for having gas to energy projects. So whereas in bioreactor landfills, because you're accelerating the waste degradation, and you're going to get substantial amount, and you have reliable amount of the gas that is generating, so you can have a gas to energy plants, and then you can have maybe some recovery of expenses from the energy that you will sell out of these plants. And then you have a lot of savings, right? You have a leachate treatment, you're not doing that, and landfill airspace gain. So as you are doing the leachate recirculation operations, doing the waste placement itself, so then waste is going to settle. You can put the more waste. More waste means more money. And then at the end, you can do the landfill mining, and then reuse the materials, and then you can use the site again for more waste use. And then this is not commonly done, but ideally you can ideally the waste organics is gone, and then you have all the inorganics, and you can do the landfill mining, sorting, and the material processing and recovery that can happen. So that's whole thing about it. Okay, but we have a lot of researchers, in the audience, but still, this is a topic that needs a lot of research. Now, some of the research needs are, how do we optimize the leachate recirculation? Okay, injection pressures, and ultimately achieve that uniform required moisture distribution in the waste. Okay, yeah, this is a really big challenge because, as I mentioned, the waste is highly heterogeneous, and it needs to be properly designed. And how do we predict the spatial and temporal variations in the gas generation, leachate quantity and quality, waste settlement, and temperatures and pore pressures? How do we predict? I mean, there are some prediction tools for conventional landfills, but how can we do the similar things, under this complicated bioreactor landfill operational conditions? And then more importantly, how do we predict the waste stabilization time? This is the major advantage, right? We're saying all the waste is going to be degraded, all the organics in the waste is going to be degraded in a shorter period of time. What is that shorter period of time? So if we know that one, we can, convince people to go for this one. And the regulating agencies like this one because, if you accelerate the waste degradation and waste stabilizes faster, then there is no risk of environmental pollution and exposure things, after that, right? So environmental agencies are always after, controlling the environmental pollution and exposure. So, if we can stabilize the waste earlier, then these issues won't arise later. And how do we ensure slope stability, integrity, and stability of the liner systems and cover systems under pressurized liquid injections? And also, there are not many field investigations and detailed monitoring programs. So there's, it's hard to find any bioreactor landfill that is well instrumented so that we can know exactly what's going on, with spatially and temporally. There's a need for, additional field investigations and especially monitoring during these leachate recirculation systems, how the waste is, performing, and consequently how the waste settlements and all those issues, if we can monitor it, that's good, but if you think about this waste, it's very complicated material, right? So, you have solids. Solids includes, you have inerts, and then you have organics, biodegradable solids. And then within the pore space, you have leachate, and you have landfill gas. So this is how, you can represent the phases of the waste. And, then if you look at what is going on during the bioreactor landfills, you are injecting the leachate, right? So that's the fluid flow. So as a result of that, your moisture is being distributed and liquid and gas pressures are induced, and then you have a leachate and gas flow that is happening in the waste. So this is basically the hydraulic problem. But you also have this mechanics problem, right? So you have a deformation, strains, and stresses, and constitutive behavior, shear strength that will be affected by this. And then as the leachate gets distributed, you will have enhanced degradation, you have a gas generation, and the leachate quality changes, and the gas quality changes. And then you also have a thermal processes that are happening. You're going to generate the heat, and then you're going to change the temperatures. But if you look at these things, one affects the other, right? And the other one affects the other one. So if you look at it, each one is affecting the other, and affected by the other. So it's very complicated. So we, in our research, we had a National Science Foundation project, and my student Girish Kumar, he graduated a couple of years ago. He developed this coupled thermo-bio hydromechanical model. So you can control, you can have a biodegradation model here, and then you have a flow model here, and thermal model here, and then you have a mechanical model. So they all needs to be coupled, right? One fits into other one. So if you can do that one, then you will be able to predict what happens in a bioreactor landfill during the operations. So for example, we took this model and applied to a typical landfill, which is in my state, Illinois, close to Rockford. We took just the same profile. We did a lot of field investigations on this site. So we got those properties, and this is the landfill cross section, and we assume these are the leachate recirculation wells, trenches, and we have a liner system. Everything that is at this landfill is modeled. So first thing is you have a subtitle D landfill conditions. You need to have a liner system, leachate collection system, final cover system, and then on the top of it you have this leachate recirculation systems, and you are injecting the leachate. And with this modeling, you can be able to understand what happens. How the pore pressures change along a cross section, or you can look at any location in the landfill, and how the settlement happens at different locations. You can look at that one. How overall gas gets produced. So conventional landfill versus bioreactor landfill changes, and also you can look at how the temperature changes. With the depth I'm showing at different times, right? It's a very temporal, dynamic system. So initially you might have a temperature, but with time, these temperatures in the waste are changing with the depth and with time as a result of all these complicated coupled processes. And then you can look at the settlement. Obviously in the conventional landfill, settlement is kind of a uniform, but in bioreactor landfill, wherever you have leachate recirculation happening, that's where you will see a lot of settlement taking place. So you have to worry about differential settlements a lot in case of bioreactor landfills. And you can also look at the stability of the liner system. So you have a composite liner systems. So what is happening there? The temperatures. You can look at a lot of different things. How the temperature is changing at the liner systems, and as a result, how the shear and shear displacements, the shear stresses are changing. You can look at all these things. So you can understand better, and then you can help landfill designers and operators to do certain things that will make these bioreactor landfills safe. So we also looked at, hey, how injection pressure affects, how the injection spacing affects, and the mode of injection affects. So we have investigated all these aspects through the modeling. So these modeling efforts are very useful, because you can understand what will happen in a typical landfill scenario. But modeling is modeling, right? So there are certain assumptions are made in this one. The accuracy of the models needs that field monitoring data. So as I was telling you, the field investigations and field monitoring is required, not only to understand how everything is happening, but also help calibrate the models. At the end, we need to have a simple design guidance for practitioners. So you cannot ask practitioners to run this complicated coupled modeling to get what you want. So somehow we need to finally summarize all our modeling efforts into a design guidance that people can use it. So the whole idea of this bioreactor landfills can lead to this sustainable waste management approach. So let's say you have a cell, and you put the waste in there, and then you degrade it, and then once degraded, you can mine it, and then open up the space again, put the waste. So idea is, these days it's hard to find a landfill space, right? So this one is not like dump it and cover it and walk away and have no use of that land, right? So here you can kind of create a nice cell and operate it as a bioreactor landfill, and then degrade it much faster, and then remove it and reuse it. So this way we are not we are doing the containment as well as treatment, and practicing the sustainable waste management practice. So this could be a good solution going into the future for waste management, sustainable waste management. So I have listed a lot of these references here. So if you are interested in knowing more about these bioreactor landfills, there are a lot of studies done on this, and I request you to look at these references. And I have listed some of our references also towards the end here. So you can look at all those papers that I mentioned in some of the slides here. And there are some good books you can get hold of and read them. That will give you a good understanding of this topic. So in our lab, we have done a lot of field investigations. We did lab investigations. We did a lot of numerical modeling. So I could talk about all these things forever, but I chose to talk only, in general, what a bioreactor landfill is, how it is different than conventional landfill is. I want to mention again one thing, okay? You don't want to think about bioreactor landfill if you don't have a well-engineered, landfill with the liners and leachate collection systems and the final cover system. So I see people doing research on some places where they don't even have a regular landfill and they want to do the bioreactor landfill. So no way you can do the bioreactor landfill unless you have an engineered landfill first, okay? And then bioreactor landfill is on top of that. So we have done all these things. So I try to give you a broader overview, so that everybody can understand, concept of bioreactor landfills, what it is involved in, what are the issues, and how do you design it, how do you operate it, how do you monitor it, and I gave you just a flavor to some of our modeling work. But there are a lot of things that can be covered in this one. But make sure whenever you are reading some papers, see if it is of practical relevance or not. There are a lot of studies that have been published, but many of them are not very useful. So I know I covered a lot of stuff, and it took more time. I haven't paid much attention to the time that I have taken, but feel free to contact me. This is my email address. I'm on Twitter, Facebook, and LinkedIn, so you can feel free to join. A lot of our publications, you can find it on my website. So go into this website and go into the publications, and you will find information on our publications. So please get hold of those and read them. If you have questions anytime, just feel free to email me. I will be happy to answer any questions that you have. So with that one, I want to thank everyone for attending this last webinar, and I will stop sharing here. And then I will, stick around. I will answer any questions that you have. I know some of you have to leave, so I'm okay, if you want to leave. But whoever is around, I will be happy to answer questions. Thank you very much.